Hello, I am Michael Spencer, and I work for Sony Interactive Entertainment, or Sony PlayStation. I work on the compiler toolchain for the PlayStation 4, and I'm also a member of the C++ Standards Committee. And today we're going to talk about object files and how linkers implement C++. So you've got your build pipeline, and you're going to start with some source files. Each one of these is a translation unit. You've got b.cpp and c.ppp, and your shared header. So the compiler looks at each of these in isolation and generates an object file. Here we've got b.o and c.o. So this is just part of your program. You've also got a bunch of libraries. Your C++ standard library, C standard library, any runtime libraries, and any other libraries you're going to link against. And it's the linker that takes these and converts it into an executable. Today I'm mostly going to focus on, right here, how the compiler is going to lower from your C++ code into the object file and what that looks like. So what is an object file? Object files can be really complicated. There's a lot of details involved in the ABIs and a lot of backwards compatibility and cruft. Some of these things are like 20, 30 years old. So when you come down to like the highest level, an object file consists of three things. There are ranges of unsplittable data, and these are commonly known as sections, or in Mach-O as atoms. Then you've got a list of names that define or reference these data, and these are known as symbols. And a list of modifications that need to be applied to the sections to reference these symbols. So let's take a quick look at an object file. So we've got our trusty compiler here, and we're going to compile our b.cpp, generate b.o. And let's take a look at it. What tool we're going to use? Well, let's try cat. That's not the most useful thing I've seen. This actually isn't cat, this is Vim. Like, cat doesn't actually print out that much stuff, it's a bunch of spaces. But we can see we've got elf up there, some Clang version info, and a bunch of strings. And it actually goes on for much longer. This file has not much in it, the C++ file, but generates a lot of object file. So we've got some tools to help us. Objdump, nm, lvm read obj. These are generic dumpers that are bin utils and LVM that can dump pretty much anything. We've also got format-specific dumpers, readelf, otool, dump bin, and see here, these are the three formats I'm going to cover, elf, Mach-O, and PECOF. So let's try using one of these tools. Go back to our source file, and readelf. So here we're passing S_R, so that's dumped the sections, symbols, and relocations. So we're going to get to what all this means, but using these tools is the first step to understanding what's in your object files. Let's start with a really simple example. This is about the simplest I could get that is still a C or C++ file that is the easiest to link. So we've got some assembly here. This is a really simple assembly. This is the x86 64 Linux ABI for calling exit and passing a value. So we can compile it into an object file. We can link that object file. And this is the whole link step for this example. If you actually look at a link, like if you pass -v to Clang on a normal build, your link line will be 1,000 bytes long or longer. It's including all of the standard libraries, all the search paths, everything that's needed. Here, we're just compiling just this file. We can run it and echo at the return value, and it's what we asked for. You can also dump it. So here's objdump asking for the disassembly and relocations. There are no relocations here because we're not referencing anything else. All we're trying to do is run this assembly. You can see the assembly, it's copied basically, almost exactly, except for it converted it to hex. And we've got our first thing, a section. So this is the text section. So let's go into sections in a little bit more detail. The most important part of sections is they're atomic, and they can be moved around relative to other sections. And this is important because when the linker or when the compiler compiles your object file, you're going to get your code and data and debug info and a bunch of other things, and they're all going to be in your object file like this, and you've got a bunch of object files. And if you just try to concatenate all those together, you'd have a bunch of text and a bunch of data, a bunch of debug, then text, debug data, and that's not very friendly for running the code. It's difficult for the loader. It would be bad. So what this actually allows is that the linker can combine sections and group them together. And it does this based on the name of the section and type of the section and some flags. And by grouping them together, loader can just look at that file, can immap it, just map that file page into memory, and then it's done. So let's take a close look at sections. Here's the section dumps from different tools. The main parts of sections, every section has a name, text in this case, has a type. So ELF is a little different here. It doesn't, the type is just prog bits for both data and code, but Mako and PCoff has a separate type for that. We've got a virtual address. Now, we're looking at object files here, not executable files. So your virtual address is just going to be 0 because the compiler doesn't know where this is going to be loaded in memory. So it's just going to stick 0 there for now. We've got a file offset. Because sections in the file are actually represented. There's a bunch of section headers, which are little things all in a table that point to big chunks of data down later in the object file. We've got the size, some flags. These flags are going to be your read, write, execute, and there's actually a couple of other flags. And alignment. And alignment's important because let's say you have a string, which happens to have an odd length. And you also have an array of ints, and these are both globals. And if you just took that, the data, the array of ints, and stuck it right up at the end of the string, you would end up with misaligned ints. On some systems that's okay, on other systems that's bad. So in order to prevent that, we have to know what's the alignment of the section. We've also got symbols. And in our early example, we had one symbol, and it was start. So a symbol defines or references a location. And symbols, they've got a value. Value is a little weird in symbols because it's not just actually its location. The value can also represent an absolute virtual address, or it can represent the size of things. And it depends on its usage that determines what value means. And in this case, it's all the offsets. Here they're all 0 because all of these symbols start at the beginning of the section. Also has a type. And type can influence how linking works. You'll notice here that Coff decided not to give it a type because it doesn't actually matter in that case. But for otherwise, it's a function. It's got a scope. This is what other object files and shared libraries and stuff can see this function, or this symbol. So here it's global, external, global. That means that every other object file can see it. And if we, for instance, had 2 globals with the same name in the same in the same link, you'd get an error because there can only be one definition of it. Then you've got a location. This is the section in which the symbol is contained. And of course, a name. Let's take a closer look at that name. So that name is actually pretty weird. It's got this _z3 PTSV. But actually, that's what the definition comes from. It was just int PTS. So there's both the Itanium mangling and the Windows mangling. I was going to explain a little bit about the Itanium mangling here. You can actually get really deep into it. It's kind of complicated, but there's a prefix, _z, string length, the name, and then void, because it doesn't take any parameters. And generally, you don't want to look at these directly. You'll like CPP filt, but if you spend enough time staring at like compiler and mangling and stuff, you kind of sort of just start to see this stuff. So let's go back to our really simple example. What if we want to call a function? So let's refactor our code, take out that assembly. You might want to call exit from somewhere else, and compile it again. So clicking, and this time we're going to pass f function sections, because I want to show you how separate sections work. If I didn't pass this, they'd all get in the same section, and it'd be hard to explain. So let's dump, same dump. Here it looks very similar. We've now got our z4 exit v, which has the original code, and we've also got a relocation, this jump. So you'll notice that we've got a bunch of zeros here. This jump instruction right now is saying just jump directly after it. That's not terribly useful. That's not really what we want to do. So the compiler leaves a little note to the linker. It says, replace this offset with the value of whatever exit happens to be -4. -4 is just because of the way x86 addressing works, is that the address in there is actually the address of the next instruction, so you need to subtract the 4 off. So it's a relocation. Relocation is, it's locations in section data that are going to refer to symbols. And there are notes that the linker leaves that says, hey, you need to go and update this once you know the final address of everything. And you can look, you can dump some symbols. They've got location. In this case, this is going to be the offset in the section. As for relocations, storing the section that you're in, each section will have a lot of relocations. So duplicating that in the section would be, or in the relocation, would be wasteful. So instead, you'll have, each section will have a table of relocations. You've got a type. There's tons of types. These are all the instruction pointer relative relocations across ELF, COF, and Mach-O. And you've got the value, and that's the expression that this relocation represents. So let's go a bit further and say we want an external function. We're gonna split our program up into multiple translation units, and we'll grab this stud_exit. Grabbing this because this is the lowest level exit that's provided by the standard library. It doesn't do any cleanup. It pretty much just calls the syscall exit. Compile this, and let's look at the symbols and relocations. First thing to note is that our exit now is undefined. It means that this exit symbol is not contained in the object file. It's got to look elsewhere. And we still have a relocation. So we can run it, get the same result. Let's go a bit further, and let's take let's make a global variable. Global variables are actually pretty simple. You'll compile it again and look at it. And so, additionally to our call to exit, we've got this new one, which does have a location. It's in section 5, which happens to be .data. It's also got another type of object. And we get another relocation into ret. And if we dump the section contents, we'll see .data, which is section 5, has these bytes in it. Those happen to be that same value, just in hex. So we didn't actually have to run a global constructor or anything. The compiler just stuffed it into the object file. And so far, all this will work in C, basically. And run it, get the same result. Let's go a step further, get some real C++. We're going to use a global initializer. And we're gonna print out a value. Teacup. So compile it again, and try to run it, and nothing happened. Where'd our output go? Well, notice I've been using start, _start, not main. A bunch of things happen before main, actually. And that's why your global initialization happens, and a bunch of setup, TLS. So let's actually see what this object file looks like, and how the compiler is trying to get the linker to do this. So let's dump this. So we actually got these new sections. We still have our original text.start, which is where the call to std exit is. But we've also got text.startup and .initArray. And .initArray has a new type, an array type. This is special for the compiler. And if we dump that section, we'll see that we've got 8 bytes of zeros. That's because that array, location will be replaced by this relocation saying, stick the absolute address of .text.startup plus 20 into there. And we'll see what happens in a sec here. Yeah, that relocation and where it points to. So I think this is duplicated. Oh, no. So yes, if we switch over to main, then it works, it prints. Except we didn't print the Unicode because, Unicode's hard. So let's go take a look at this thing. And so we've got our section and the relocations. And then your libc is going to have some code like this. What this code does is the compiler our init array is special. It's part of the semantics of our API. And so it puts an init array start and init array end symbols into your final executable. And then your libc will contain some code similar to this. And all this does is treats it as a function array. And because of the way the linker works, taking all of the init array sections, they all have the same name, so it just concatenates them all. And then at the end, you're just left with a list of an array of function pointers. So it's actually pretty fast to set this up. No special processing and weirdness. Let's make this a bit more complicated. Let's say we want to refactor again. We're going to have this shared init function. We want to call this everywhere. So, but it's inline. And let's just say this isn't a header. We've partially preprocessed this code, but the inline is grabbed from a header. So we'll compile it again, and we're going to dump some stuff. So we're going to look here, and this is just the sections. And we've got a new flag here, this group, or G, which means group. And if we look a bit further, we've actually got some comdat groups. What this is saying is that the section for the init and the relocations for that section are part of a group, and that they go together. And that if you drop one, you need to drop the other. And each group has a group name. And I'll explain a bit how that processes in the linker. We've also got a symbol, and this symbol has a new type. So instead of global, it's weak. A weak symbol, you can actually have multiple of them, and the linker just chooses one. And so the way this works is comdat groups. And each section can belong to a group. And so here we've got they're both in group ZInit. And when the linker is reading in object files, it inserts this group name into a table. And if it's already seen that group name, then it just doesn't load it at all. It just ignores them. It just drops them on the floor. So that's actually really fast to process instead of having to go back and try to match identical functions and merge things. That gets complicated. And this is actually where the one definition rule comes in, because there's no information for which one of these from separate object files the linker should pick. The linker can pick any one of them, and your program has to behave the same. So that's why all your definitions in the source code have to be the same. And we can actually take a look at templates. And so maybe we want to return a different type, although int's going to be the only valid thing, basically. But from the perspective of the compiler and linker, this is exactly the same, except for the name has changed. It just has a different mangling. That's the only difference. So let's make our global even more complicated and make it inline. So C++ 17 feature? Yeah, 17 feature. So we can compile this and take a look at it. And some new things here. We've got the BSS section, which is just, and no bits, which just means that this ret is going to be 0 at the beginning. So there's no reason to store this in the object file. And no reason to store it in the executable, actually, either. This tells the loader that when it loads it, that it just needs to allocate lots of zeros. In this case, it's only 4. But we've also got this weird extra thing, GV. This is a guard variable, because every object file that emits this inline variable needs to have the constructor for it. You can't actually remove that because this might be going into multiple shared objects, and the shared object order of initialization might be weird. You might be like loading a shared object in a thread. And so it needs to have a separate variable that can do atomic, hey, have I initialized this yet? And we've got weak there, so we'll only end up with one of them. Now if we go back a bit and change this to a static function, you'll note that there's no comdats, and it gets local. So this is why you don't want to have static functions in header files, or namespace, anonymous namespace scoped things in header files, because this function will be duplicated in every object file and requires additional linker optimizations to maybe get rid of them. Linking inline functions and getting rid of those is much faster than than hoping the linker gets rid of the static. So let's talk a little bit about debug info. So I could give a whole talk, multiple days, about debug info. But there's two main debug infos now, formats. There's dwarf, which is used on Elf and Mach-O, and codeviewed/PDB, which is used on PECOF. And so the way debug info works is that it's a collection of sections that are just mapping source code to object code. And the compiler emits a ton of data, all your types, all your source ranges, and sticks them into these sections. And it's the linker's responsibility to deduplicate data and to provide any indexing to help the compiler. Now, this can slow down your linker, and so there's generally options to either enable it or disable it. It's a trade-off between how often you're building versus how often you're starting your debugger. Let's take a look at exceptions. So here's some beautiful code, uses exceptions. And we've got some external calls to make sure that the compiler doesn't just totally see that, oh, you're not actually using the exceptions, nothing bad can happen, I'm just going to remove all the code. And exceptions, they're all, today, are all table-based implementations. And the Elf and Mach-O are actually based on dwarf. They use some dwarf tables. And PECOF is a totally custom format. But they work similarly. So we're going to take a look at the Elf implementation. And basically, here's what you get. And so you've got the GCC exception table, which actually contains the special data for the catch clauses. And that is the C++ runtime data that's needed to figure out which types are being thrown. And you've got the EH frame, which is actually the information for how to properly unwind the stack. And that is generic. It's shared by languages. And then the accept table is per language. And then you actually bring in a whole new library, so all these undefined symbols. Got to be able to unwind, allocate exceptions, catch, and throw, and this personality thing. And that's what checks to see, hey, do I need to catch at this block? So I'm going to explain how static linking works at a very high level. There's a lot of details that go into this that makes our ideal linker not actually work that way. But you basically have 5 steps. You're going to read, input, resolve symbols, layout, write, and apply relocations. So we're going to read your input. So you open up every file in the command line and record all the metadata. So you record the sections, symbols, and relocations. And for archives, or static libraries, you actually just record its symbol table. Then you step in and you start resolving symbols. So for each symbol, you need to determine which symbol is the actual primary symbol definition there. So you saw we had weak symbols earlier for inline and stuff like that, and templates. It actually needs to choose which one of those is going to be the main definition. And it just picks one. Generally, it's going to be the first one it sees. But if you later have a strong definition, it'll pick that. And at the end, if you've seen 2 strong definitions, you need to error. And if you haven't seen any definition, well, you need to error because you've got an undefined symbol. Then you need to start laying out sections. So you're going to group sections by the types and flags. combine inputs with the same name prefix, and then assign virtual addressings while respecting the alignment, as I was explaining earlier. And at this point, you'll know the addresses of all your symbols. And then you're going to write your output. So this is actually pretty simple. You're just, for each input section, you've already determined where its addresses are going to be in the output, so you just memcopy it, basically. But after you've done that, you're still going to have these references of like call 0, and that's wrong. So you need to apply relocations. So for all of your input sections, you've got to go over them, look up the symbols it references, and then compute the result and write that into the output. So you actually like write twice. So while you're doing all that, there's a bunch of linker optimizations you can do. ICF, or identical code folding, relaxation, some others. So let's take a look at ICF. So you've got these two functions. Let's assume that A and B have the same size and have trivial constructors. This code is probably going to look the same. Without ICF, you'll just get two definitions of it, but with it, you can merge them. So that just looks for identical sections, and there's a special bit to this. So you like the same byte, same type, same flags, but not the same relocations, not necessarily. They need to be equivalent. And so you actually look at the full relocation graph, walk the whole thing, make sure that all the sections have the same bytes, same types, same flags, and equivalent relocations. And then if all that works out, then you can merge them. And the algorithm is actually kind of tricky. Rui, one of the Google guys that works on LLD, actually came up with a really good algorithm for this that beats everyone else. It's pretty fun for LLD. But after you do that, it picks one and discards the rest. So relocation relaxation. When you actually write a call like this, and you're generating position-independent code, like you're going to write, and you're doing a shared object or a DLL, it's actually going to look like this. This is an indirect call through the global offset table, which I'll get to a bit later, but that's basically a table of addresses that'll get filled in later. Now, if the linker knows that this function, it actually knows the full address of it, it can just convert it to nop call foo. And you have to insert this nop, because remember, sections are atomic. You can't just like cut one in half, take out a byte, and glue it back together, because you might disturb all the other offsets. Also can do this very similar thing with TLS relaxation. So there's actually this really kind of complicated way to get to a TLS, a thread local storage variable, where it might be anywhere. It might be just a shared object, initialized somewhere else. So you've got to get the descriptor for it, and then that's actually a bunch of nops, and then call get address. And if the linker knows that, hey, I actually know where that global variable is, or where that thread local global variable is, I can actually just convert it into grab the TLS address and then just compute the offset and grab it directly. And that actually helps a lot in certain circumstances. You've also got special sections, which are merge sections. These are sections that are known to basically not have the address taken of certain things, and these are generally going to be strings and sometimes fixed data. And this is actually much simpler than ICF, because you just here the section is actually not atomic. You can split it up all you want. So you can split it up and do a unique on them. Next thing is garbage collection. So you've got your big libraries. You've included Boost, although Boost is actually really a problem here because it doesn't have much object code, but certain libraries. And you're not actually using the entire library. You're only using parts of it. So what's the point in including all this code in your final executable? You got to ship that to customers. It's bad. So what garbage collection will do is, first, you got to find all the roots. So like your start, which is actually where the entry point of your program is, all your global constructors, and a ton of other things. Then you just do mark sweep. So you mark all the sections that are reachable, and then remove everything that's unmarked. And then a fun one, link time optimization. Again, there's actually, I think, been talks here about link time optimization. But how this actually works in the linker is that you delay object file generation until all inputs are known. And you have to do this because you actually want to, there's additional optimization that can happen in the linker that is only possible because of, you're able to determine which symbols are needed externally. And so there's this pass that you run, which is in LLVM, it's called internalize, which tells the optimizer that, hey, these symbols, no outside code is going to reference them. So you can see everything. So all the code you see is everything that touches it. And this actually allows it to do a lot more optimization and reasoning about the code. And so you make them internal, optimize, then generate object files, and then pass those into the linker again. Dynamic linking. So once the static linker is done, that runs on your dev machine, you got to ship this to somebody, and they need to load it, and they need to run it. And this is actually done by dynamic linking. And there's a lot of parts of dynamic linking, but the core parts are loading it, applying relocations, and then this thing called the PLT GOT or IAT. So to load the binary, your kernel, the executable contains a bunch of instructions for the loader. They're called different things in different formats, but essentially what it is it tells which bytes of the input image need to go where in virtual memory, and which flags it needs. And this is generally just turns into a map call of the range. You've then got to do some dynamic relocations. You might have address-space layout randomization, or you're loading a shared object, and so you don't know where it could be because you don't know how many other shared objects there are. And so this is for everything that can be a cross-module reference. You need to have these relocations. And so they're applied after everything's loaded, and generally not allowed to relocate executable bytes. Now, since you're not allowed to relocate these executable bytes, you need some way to get around that. And the way that works is the PLT GOT or with the procedure linkage table and global offset table on like ELF systems and Mach-O, and the import address table on Windows. And all this is, it's just a table of addresses. So it's basically a function pointer array, or a pointer array. And these are relocated sometimes by the loader at the very start, because you have no knowledge of when that access is going to happen. But for functions, it can be lazy about it. And it can call, so that's what the procedure linkage table is for. It'll jump in there. If it hasn't been called before, the loader will go and run and find that function and store the address in the global offset table, and then jump there. And then all future calls will just jump directly to the new function. So I have. Any questions? No questions? Oh, we have a question.
We were talking about template functions, non-inline template functions, and how it, checks that the bytes match and everything. What if the bytes don't match? What if you put an if-def so that the template function is different depending which file you were in? So you've got two template functions with the same signature and the same names. Mm-hmm.
So the question was, what if you have two template functions which actually aren't the same? So it can really depend. In this example, if it's simple and there's nothing else referencing it, and depending on certain offsets, it can actually just work. But it's really dangerous. So that's where the one definition rule comes in, and so it's undefined behavior to actually have different token ranges.
Yeah, it'll just pick one at random. Right?
But there are cases where this is wrong. Like, for example, if the debug info might be wrong, it might pick a different debug info than it picks for that
Things.
So your debug info might be wrong. Your exceptions might be wrong, which is pretty bad.
Format your hard drive because it's going to be
Yeah, exactly. It's going to format everything.
So most of this stuff happens once on the build machine, but the dynamic linking obviously happens every time the program started. What are some best practices specifically in C++ for reducing startup time as much as possible and keeping the amount of work the dynamic linker has to do down?
Well, for startup time itself, best thing is don't have any global constructors. But in terms of the actual dynamic linking, a major thing is visibility. And so if you have everything, so by default on Linux, everything can be interposed. And that means that all functions have to go through, and all data has to go through these tables. If you change to hidden visibility, which means that you know that this object is not used outside of this module, either your executable or your library, then the linker doesn't actually have to generate dynamic relocations. It can instead just resolve those all at compile time, or sorry, at link time, at static link time. So hidden visibility, don't have as many globals, and those are really the major things.
Thank you.
So just a clarification question. You're suggesting not to use static functions and rather use inline functions, right?
Don't use static functions in header files. If it's in a single translation unit, that's fine, because there's only going to be one of them anyways. The problem is that when they're in header files, then they get duplicated into every object file, and then you're relying on optimization to catch it instead of semantics.
What about class static functions?
Class static is completely different, because those aren't actually local. They are, the static keyword is heavily overloaded.
Okay.
So yes, yeah.
When can you rely on comparison of function pointers when the function pointers come from instantiation of templates, potentially among many different object files?
The standard guarantees you that that's going to work. And it actually does work on Linux. There can be problems with the way that Windows implements it. I don't remember under which circumstances, but you can get cases where the addresses won't be the same. But on Linux, it actually makes sure that every object file references the same one. And that's how like the weak symbols help with that, because there can only be one definition, and they'll all end up with the same one.
And it doesn't matter whether it is shared objects or statically linked from several modules?
Nope. On Linux GNU systems, it doesn't. I'm actually going to read. Do you know if that's an issue on Windows?
Yeah, they're not going to be the same.
Yeah, so they're not going to be the same on Windows. And you actually, if you do default visibility equals hidden on Linux, they also won't be the same.
All right, so I've got a question on identical function folding. So let's say to keep things really simple, I'm compiling with O0, and obviously I've got like 50 different vector dot sizes in there. Those all have to have a different address.
Yes.
How is that handled?
So the way you actually handle this is there are ways to know if the address is taken or not. Like the LLVM actually has a special linkage for this, like ODR not taken, or address not taken. You also can look at the relocations that are used to get some hints. And the last step is you just add a nop. So you just have a series of nops at the start. And so they all have different addresses.
Oh, so you're saying function addresses are not necessarily aligned? Because if you're able to jump to a nop...
Well, you might have a 4-byte nop. It depends on the processor you're on. But yeah.
Thanks.
I have the problem when I link against libraries from Boost that my RAM gets filled up with a bunch of 50 variables called ID. And
50 variables called
ID. and these are statics within a template function somewhere, and I'm not really good at the linker. How can I make those go away?
So I'm not familiar with this exact problem. Where are they coming from? Like, what C++ construct are they coming from?
It's a templatized function with a static pointer in it.
So with a function local static?
Yeah.
Okay. Well, those all have to be different from the language. You're not going to get rid of them unless they're not used.
Well, they aren't used.
So if they're not used, why is the linker? Which platform?
ARM for Thumb2 Cortex microcontrollers.
Okay. So it's really going to depend on the linker and if it's allowed to GC it or not. I see no immediate reason that the linker should not be able to GC it, especially because you're not using shared libraries and stuff. This is just a static link.
No, this is static link.
Yeah. So the linker should be able to remove those. I can't tell you why it's not without looking more into it.
Well, I have a slight suspicion it usually has to do with some kind of stream buff libraries where there's somewhere virtual functions under the hood that, like, it probably can't be called. I turn on LTO, they don't go away. I turn on everything I find, they don't go away.
Even LTO doesn't get rid of them. I would have to see the specific example, but can the tools help you? You could go and look at what the symbol linkage is, and you need to go look at the relocation graph, and there's not really a tool that'll just show you the relocation graph. But if you want to dig through that, you can try and find the relocation that's to those that the linker can't get rid of.
Yeah. Okay, so I have to learn this stuff, basically.
Yeah.
Okay.
That would be my suggestion there. Yeah.
Well, on multiple occasions I ran into this problem that I defined some sort of structure in a CPP file and called it say foo, and then also defined the same structure in a unit test, same name, and the linker was like just fine. Well, I'm going to link this together, but as soon as I ran it, I obviously got segfaults and just completely blew up. And do you think it would be possible somewhere in the future to add some, mechanism to warn the user that he's doing something that's going to blow up?
So.
Or is it impossible?
Well, so I'm surprised that you didn't get a link error. So were these structures defined local to the function or just globally?
Well, they were globally defined both in the CPP files. But well, what I should have done was to use anonymous namespace, but well, I didn't.
I'm just a bit surprised that you didn't get an error from it. I would again have to see the exact code, but there is some work being done and Gold has a bit of this for ODR checking, where it'll actually, if two things have the same name, it'll also actually include, I think they implement it by including a hash in another table, and they'll go and look up there. So there is some work being done to catch those cases. It might not be that exact case, but cases similar to that. But it does add overhead, but there is some work going on there.
So should I file a bug report if this happen again, or?
Yeah, you can, it's going to be a feature request, but well, maybe. You could file a bug, and then with a test case, we'll be able to say, oh, this is actually a problem, or no, this is something that we need to check for, and we'll add that to our checker.
All right, thank you.
So I was wondering if you can speak more about the parallelization of the LTO step, because everybody always says compilers can be multi-threaded. No. But then suddenly you have this step where apparently that's not true.
So were you at Teresa's LTO talk, or thin LTO talk?
No, I'll watch it on YouTube.
Yeah, so watch her talk. You actually can also parallelize monolithic LTO, which is, it's hard. Like, parallelizing compilers is hard. But we actually do, like Google actually does have like a working parallel implementation. It does some tricks of sharding and stuff.
Hello, I just want to say that the ultimate tool to catch ODR violations is Unity builds. I mean, if you support that thing, it works for everything. Yeah.
Yeah, that also works.
Unless you have files that on their own require like 10 gigabytes of memory per file. And
Yeah.
When
Stop writing crazy meta programs. Okay. If that's it, then. Oh.
Questions. As far as I know, there are multiple linkers around there. So it's LD, LLD, gold as well, right? Can you outline the difference and why would I want to use one over another?
So if you're on Linux, you basically got 3 options now. And LD is pretty old. It's going to have the maximum compatibility and compatibility with all of every linker script ever written, and that's going to be for compatibility. Goal is going to be faster than LD and is going to have a bit lower compatibility. There's some things that they were just like, no, that's a bad idea. We're not going to implement that. But it works with pretty much everything, and has a few more features. LLD is actually generally going to be the fastest. It doesn't have, it's pretty feature complete at this point. There will be a few more either unimplemented things or maybe a few bugs in linker scripts. But I would highly suggest you try out LLD, and hopefully it works for your project.
Thank you. Just to clarify, when you say faster, you mean link time performance or runtime performance for application?
Link time performance. The linker will do some things to change link time or runtime performance, but at this point, all of the linkers implement basically all of the relaxation strategies. LLDs, if you're on ARM, for x86, this is easy, but if you're on ARM, I don't know if we implement all of the best trampoline generation or the thunk generation algorithms. Maybe a few other issues. But the best thing is try and see, benchmark.
Thank you.
One more.
Does every SO have its own PLT?
Does every SO?
Have its own
Oh, shared object, yes. Yeah, yes. Every shared object and your main executable will have its own PLT and global offset table. And yeah, and so they'll get filled in. So if 2 different SOs call the same function, then they will both get a global offset table entry, and they use their own. Yes. Any other questions? Okay.